Hi, let's introduce the ideas and some concepts related to light-emitting diodes, It's that kind of a special diode that has an open junction and they are organized and built using special semiconductors like gallium arsenide. And so they work in a way that you can see the light or no light. So you have a 1 and a 0 in some way. So this is a perfect device for just representing digital values, or they are in very different formats. This is the typical diode, the red one, and this is a kind of a flat, surface mount device. And then you have even lamps, power lamps based on lamps today, in which you can modulate the light intensity as well. Or the typical format, in this case, LED, associated to every single segment in a 7-segment displays, or even this dot here in the decimal point, or the 2 points, used to mark seconds in a clock, those are LEDs. Every single segment is a LED. So the point now is how to connect LEDs in digital circuits. Which is the interface? How can we do that? That kind of connection that is so used everywhere and in all kind of instruments and devices. So hi, let's solve this concept that is attached, it's connected to the previous videos or the previous ideas on voltage margins and the like. It is the idea of driving LEDs, okay? What you have to do to observe, for example, by means of light and no light, what is a 1 and what is a 0? You may imagine that thing. A light, true, no light, false, or whatever, but making that difference. So the device that will allow you to do that is, a LED. So a LED is nothing but a diode, but that has the union, the junction you see visible, and this manufactured using a mix of semiconductors, that you can see the light when biased correctly. So let's see how can you bias a diode. So the typical circuit is, for example, if you like to connect that circuit now that is driving the LED with the previous ones, which was a gate, for example, a 74 gate that is 74LS04. So you have a gate as before connected to a push button that has been studied before. So you see you are able to generate zeros and ones here, that the gate adapts and generate voltages at the output. So the voltages at the output can light or no light the LED, that's the point. And that depends on the circuit. Doesn't matter if this one or the other, in some way or another, and using NOTs or buffers instead, you can very well connect the LED like this. You see, this is the anode and the cathode. So this is the cathode connection to the ground. The people call that common cathode connection. The cathode goes to the ground potential, you see, the ground voltage. But in this way, in the other way, you have VCC, and the anode is the one that is connected to the power rail, VCC. So this is the common anode connection. Now is not important but when you have several of them, for example, when you are talking about 7-segment display to represent digital, decimal numbers, you have 7 of them in the same device, generating the shape of a number. You have 7 segments, and every segment and the decimal point is nothing but a LED. So there you have them all connected to a common cathode or a common anode. That's the situation. We will see the circuit to drive this device later on in project 2. It's a kind of a standard circuit, a driver for you know, lighting 7-segment displays, a very common and very well-known circuit. But now you see here, you only have 7 of them, or 8, considering the decimal point. So let's talk about the single one, the red LED or the green LED that you may imagine. So if this is what you've got, you may imagine a green LED here, for example, okay? This may be a green LED. So what is the situation that is generating green light, for example? In which situation you generate a green light? And imagine that this one is red, okay? This is the red LED. So in which situation this circuit is going to be, will generate light, I mean. So in which situation? So for example, now that you are not clicking the button, so what you've got, you see, is a 1 in this circuit. When a 1, that is a 0 here. If you have 0 volts here, you have an equivalent circuit, which is 0 volts. Well, 0 volts, do you think so? No such a thing as 0 volts. You have VO low battery. It may be, remember, for this technology, it may be as high as 0.5 volts. So you have a voltage here that is not strictly 0. And that is some way the equivalent of the gate, if you see the gate from the output side, with a very, very low output resistance, which is practically, we don't need to talk about that. If you see the 7 equivalent is a voltage and a resistor, but the resistor may be completely negligible because it's not necessary, especially because what goes next, you see, is the RL, the limiting resistor for driving the LED. So this is what you've got. And here you are the anode and the cathode, and what happens here? Well, this is a LED, right? And a LED has this kind of function. This is the voltage anode cathode, and this is the current through the LED. You may imagine that this is the current through the LED, and what? Well, this is an exponential function, something like this. This is the threshold voltage from which the diode starts conducting. It is directly biased. So what we like here? Light or no light? Well, we like to have light, but you see, in this situation with the voltage low, for example, if this is a green LED, I guess that, for example, you may imagine very well that this is something like this, you see? Well, it's not that difference, but in some way 1 or 2.2 volts. Let's imagine that this is 2.2 volts, and you like to have this Q, this bias point, and for example 15, you see, 15 milliamps. So a typical LED, 15 milliamps, lighting in green, and to do that it has to be biased at this point in the curve, and the voltage required is 2.2. So this LED, when working fine, it's equivalent to practically a battery of 2.2 volts, something like this. So very well, when you have B0 low, this is not possible. You have here the LED, you see, this is the circuit is not 0.5, you see, the circuit is here. So when you have a 1, let me use another color to make this. So if you have a 1 here, you have a 0, right? The 0 becomes this voltage, B0 low, and you are here in the curve, for example here. So this is the Q that you've got here, no light. That's the situation, okay? The same with the red one. So if now you are not clicking, what is happening here? You have a 0, okay, because you are connecting the input of the logic gate that has these connections to the power supply VCC naturally. So you have a 0 here, and so this is a 1, logic true. But you know, a logic true is not such thing. It is what? Remember? VO high. And that can be very variable, maybe between 5 and 2.7, I guess. So in some way, if you are making such connection, what you are doing here? An equivalent circuit, which is now a high voltage battery, well, a high voltage, you know, V, let me use the same style of coloring this, VO high, the negligible resistor, and then the RL, so this is ground, this is the equivalent of the gate, like this, from this point of view, and then the resistor, and then the diode, like that, and then the VCC again. So you have, in some way, imagine that this is VCC, almost VCC, imagine that this is 4.5 volts, 4.5 volts, 5 volts, so there is not enough, forward voltage. So this is the voltage anode to cathode, this is the current, and if this is a red LED, you may imagine, for example, that you are liking to light it with, I don't know, this bias point Q, so for example 5 milliamps, and this is I don't know, 1.83 volts, to give just an example, being that one here the threshold, very near that voltage. So when you are reaching this voltage 1.8, the diode is starting to conducting correctly, so it's managing current correctly, so the current goes through. But you know, in this situation, you see, if you have a high, that is not possible, because here you have another high, so you are probably at this point. You see, no light. Now what? Well, no light. You have let's talk about digital values, no light, because it is true, you have a 0 here and a 0 here, so 0 in both ends makes it impossible to go through enough current or whatever, and here the same thing, you have 1 and 1, so there is no current flow here, the current is very low, you are at this zone of no conduction, so the diode is blocked and is not generating any kind of light. But now let's imagine that you click the button, doesn't matter, in the circuit for the green LED or in the circuit for the red one. If you click, what happens? Well, if you click, look at this, you are generating a 0. The 0 becomes a 1 at the output. 1 means that now the equivalent circuit is that one. You see, I can delete that. There is no need to keep them both, especially if this is a video. So I can delete now, and I can keep the equivalent circuit, because the only thing that changes now is that you have a 1, right? So a 1 now is the same value as you've got here, VO high. Aha, so this is exactly a 1, you see? So now the things are completely different. You have a 0 there in the cathode and a 1 driving this LED through this resistor. So now, yes, 1 is enough to be able to ubicate, you know, this is the situation of the bias point. You can do that very well. And here, a similar thing. If you click the push button, what you are generating is 1 at the input of the gate. Here you are generating a 0 at the output of the gate. So a 0, you know, is the same circuit, but now the same way. I can delete that, and look at this. The 1 is kept here in this side, in this, you know, in this side that is attached to the anode. Here you have a 1, but now the equivalent voltage of the gate is what? A 0. So you see, is VO low. that is what you've got here, VO low, okay? So what is the meaning of this? That indeed, yes, there is a margin of voltages, but this is a zero, so very well. If you have a 1 and a 0, this is going to make possible the current flow, and so this may be your bias point. So if you are, you know, polarizing the diode at this place, biasing it here, probably it will have the rated current. The light is going to be here, so that is the secret. So what is left now? What are you thinking that is left here? Okay, in this situation, what is left? Well, if you have it all, you have an electrical circuit, you have an equation. Let it be like this. Which is the equation of this circuit down there? You see, if the current is flowing, you have something like this. Let me use the black color now. You have BCC from this point, then you have BCC equal to the voltage anode to cathode, that's a voltage, this voltage precisely. So plus the resistor multiplied by the current, ID, you see. And then there is this voltage that maybe ideally 0, but now is VOL. So that's the equation down there for this circuit here. And what about the other one? There is another one. So you see, once you've got the equivalent circuit, you have to investigate which is the equation. The equation driving this circuit is such as VO high equal to RL multiplied by the current, you see, ID, plus the voltage anode cathode, and then 0. Okay, so that's the Kirchhoff current. That's, you see, you have a loop here, and that's the way to calculate everything. So what is everything? Well, the technology, you see, is giving you this voltage from the datasheet. The diode, or that one, you see, the BCC is, for example, 5 volts. BCC down there that you need it, for example, if you are using these chips, 74LS, low power Schottky, this is usually 5 volts, typical value. BCC is given, data. VO high is given as the same because it came from the datasheet, like this one here. This one is given from the datasheet. Then what? You are deciding to bias the diode at this level, 15 milliamps and 2.2. This data came the same from the specifications of a diode, okay? So very well, this is given and this is given, IDQ, you see? So what is left? The resistor. So the only thing that is up to you for calculating here is the right resistor for just generating that kind of current. In this way, you see, this gate is sourcing the current when high. You see, when high, you see, you have the gate is sourcing this kind of current that goes through the RL and through the diode and generates light in this device. And down there you have the contrary. When 0, the current from the VCC goes through the diode and goes down to the ground because the gate sinks. You see, instead of sourcing current, sinks current to the ground. Okay? So that's the real thing. So then what? Well, so if you have everything and the only value that is left is the limiting resistor, this is what you have to calculate. So the problem stays like this. Which is the limiting resistor that you need to drive the LED like that? With a connection, common cathode, and with this value. So that this is RL, you see, is VO high minus the VO high, right? Let's do that. VO high minus the voltage anode to cathode divided by the current in the diode, okay? That's it. And down there in the other equation is something similar. The limiting resistor must be what? VCC, in this, which is a common anode circuit, the limiting resistor must be VCC minus, the voltage, output voltage low divided by the IDQ, the current through the LED at the bias point that you like, IDQ, right? So very well. So something else, yes, this value has to be which one? The typical or the worst case scenario? I guess that the lower the voltage, the worse, because you have to guarantee, even if you have the lowest possible voltage here, you have to guarantee the 15 milliamps because you are going to bias down there and perhaps there is not enough light. So you have to solve the equation in the worst case scenario, which means the VO high minimum possible. And here the same thing. Even if you have, you see, if the voltage at this end goes up, because instead of 0 you have the typical value, or instead of the typical value you have the VOL maximum, you see, VOL maximum, even in this case, you have to guarantee by this calculation that you have at least 5 milliamps, so not less than 5. Perhaps a little bit more, but not less. Okay? So that's the point. So if you like to solve that for real values, in this example, the RL is VO high minimum. We calculated that as 2.7, remember? Minus the voltage anode to cathode, that depends on the type of LED. For example, the green has a different value from the red, from the yellow. But let's imagine 2 volts. And then the current naturally is determining here 15 milliamps. So in this situation you need a resistor of 33 ohms, that's okay. And if instead of the worst case scenario 2.7 you have 5 or 4.5, more voltage than that, or the typical value, which 3.5 or something, we will have this bias. You see, instead of the one that you like, you will have that one here. But that is not going to make any difference, or not that different in the, just a little bit more current because the voltage is just above the minimum. But doesn't matter. That is going to, what you want in this kind of circuits is to see the light, or to guarantee the current, okay? So that's okay. And here the same. If you are calculating this, the RL is going to be 5 volts minus the VOL maximum, and the VOL maximum, you know which one is that. Is this 0.5. All right. Okay, and here I forgot. You see how easy it is to forget terms here in these equations? Is VCC minus VOL minus the voltage anode to cathode. So in this way I've got all the equation now, because voltage anode to cathode is minus 1.83 divided by the current now, which is 5 milliamps, and this resistor is 4.5 minus 1.83. I guess that this is 350 or 60, so let me calculate it again. It is 4.5 minus 1.83 divided by 5 milliamps, so 500, this time is 534 ohms, so you may very well, this time is not normalized, and indeed it doesn't matter that much, because you may use here very well something in between, for example 560 ohm, that is okay, the same, very okay, or 470, just is going to mean just a little bit more or less current than the one that is expected, but light, okay? So that is the way to solve this kind of circuits, guys. Is that right? Do you, more or less, you can understand what is going on here? Circuit, then you have to see which kind of equivalent you have. Depending on the circuit, you have a different situation. Then you have to go through the equation, and in the end you have to get some values. And perhaps you have to normalize that, because there is no need to use two resistors here. You can pick up the approximate one, you know, there has to be that perfect. There is no need, because what you are doing here is lighting a little bit or a little less a LED. Okay, so that's the example of driving LEDs, and that's the typical situation. So now you see, when you are picking a technology, this is the kind of calculations that go around a given technology.